Okay, good morning everybody. So we are continuing this gas turbine cycle. So this is the last part of gas turbine system. So we'll discuss about binary and Rankine cycle. Before that, just recap the gas turbine cycle. It is having one compressor, one turbine, one combustion chamber, then gas is going out, air input and exhaust gas is going out. Okay, now Rankine cycle I am saying. So Rankine cycle means it is having one boiler, then it is going to turbine. Okay, from turbine we have one condenser, then from condenser again it will be going to boiler but through pump. Okay, so in Rankine, this is Brayton cycle. So in Brayton cycle, exhaust burned gas is going to turbine and turbine blade is getting energy. But in Rankine cycle, your water is giving steam, so that steam is driving turbine. So the basic difference is that in Brayton cycle, the burned gas is driving turbine, so there is no water here. But in Rankine cycle, we have you are burning fuel, but that fuel directly is not going to turbine. The other water, what steam is going to turbine. Okay, now in previous lecture we have seen the reheat cycle for Brayton cycle. So compressor is here, turbine is here, then again another turbine. Okay, so combustion chamber here, entry, then again before going to second stage of turbine, second level of turbine, you are reheating again. So you will have combustion chamber here again, or the heating source, so that temperature will be going up here. You take fluid, it put here, again from here like this. Okay, so 1 2 3 4 5 6. So you can see this reheat cycle. This is reheat cycle. Okay, now if I say intercooler, with intercooler, so again you draw the gas turbine system. Okay, so first stage is taking air, then here heat exchange will be happening, so heat will be going out, heat out or cooling before going to second stage of compressor. Okay, compressor 1, compressor 2, turbine 1, turbine 2. In this case only one compressor was there. In first case compressor, turbine 1, turbine 2. So this is again from C2 we are sending it to heat source or combustor. From combustor turbine, turbine 1 to again is going to some heat source, combustor or some heat source, from heat source to turbine 2, turbine 2 going out. Okay, so this is intercooler, this is reheating. Okay, so in previous lectures, for example in pump section or turbine section, we have discussed that if you have one single stage compressor, and that will be taking more energy to compress same amount of air. But if you have intercooler, then compressor performance will be increasing. That's why we do intercooling application, or we reduce some heat between every stage of compressor system. In turbine again, if we can increase performance if we reheat the system. Okay, so that's why one turbine system can have multiple intercooler, multiple reheating system. Now if we have intercooler, reheating and regenerator also, so what is happening in intercooler? You have to compressor 1, compressor 2, then in between there is heat rejection process, then it is run by one turbine system, maybe multiple turbine also possible. Okay, now C2 to your heat addition is happening, is going to turbine 1, turbine 2. So what is happening, turbine 1, turbine 2, whenever heat is getting rejected, so that heat will be given to here. Okay, and in between there will be intercooler also. We'll say Q1, maybe Q1 dash 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so from there again it go out, or it can be directed to 1. Now you can see process 1 to 2 compression happening, 2 to 3 you're releasing certain amount of heat and you're putting into compressor 2, so that total compressor performance will be increased. Now from C2, the compressed air, it is going to a combustion chamber. So 4 to 5, okay, 4 to 5 here. Okay, so 4 to 5 your combustion chamber. So combustion chamber is adding lots of heat. Okay, now here I have done one mistake, I have to correct it. It will not be here. Rather, turbine 2 will be giving heat here. Okay, this is your heat exchanger. So 9, maybe this one 10. So 4 to 5, instead of 4 to 5 I have to put 5 here, I have to put 6 here. You have to change the numbers, 7, 8, 9, 10, 11. So 1 to 2 compression happening, 2 to 3 intercooling happening, 3 to 4 again compression happening, 4 to 5 actually heat exchanging happening. What is happening, T2 rejecting lots of heat, exhaust gas is going out from T2, so that high temperature fluid, high temperature exhaust gas will be used to increase temperature of compressed air, because compressed air C2 to combustion chamber is going. If you can increase certain amount of temperature, it will be beneficial for us, so we can recover some amount of heat from exhaust gas. Okay, so there is called regeneration generator. Okay, just to increase whole system performance. So exhaust gas temperature or heat will be used to increase temperature of my compressed air, so that compressed air will go to combustion chamber. So 5 to 6 combustion happening, 6 to 7 not required actually, so 6 to 8, you can say 6 to 8 turbine is taking power, 8 to 9 you are reheating, you are giving extra heat, and 9 to 10 your turbine is taking power, 10, you see 10 is exhaust actually, turbine exhaust. So turbine exhaust is heating your compressed air, then it is going out. Okay, so this system is having all this intercooler plus reheat plus your intercooler reheat and regeneration. Okay, all these techniques or mechanism used to increase whole system performance. Now actual system will be more complex, because this is we are showing line diagram, but there will be lots of control valves and fittings and other arrangement, insulation, many things are there, we are not showing here. These are the basic cycle, how the fluid will be flowing and how you are getting power. Okay, now binary cycle. So naval ships, a submarine powered by nuclear fuel, pressurized water reactor. Normally there will be one energy source. Okay, reactor. So reactor in steam turbine system, it is a boiler. Okay, but it is having very high temperature. Temperature will be so high, so directly normally we do not put water here. Rather, we will have one secondary fluid. Like say fluid 1 will be taking heat. Okay. So let's say this is taking heat, and now this fluid is having very high temperature. Okay, because reactor nuclear reaction, it is giving very high amount of energy and temperature very high, so that high temperature and that radioactive environment will not be putting any water, any other fluid or any our working fluid. So one vacuum fluid will be there just to circulate or take heat from the reactor to my actual system. Okay, so now let's say we have one heat exchanger here, and now we'll have boiler system. Okay, condenser, then pump, okay, one or A and B. Okay, so cycle A may or may not be producing power. Okay, cycle B actually my Rankine cycle. Okay, so in normal nuclear power plant will have one dummy cycle and one Rankine cycle. So Rankine cycle will be extracting energy. So your naval system, especially for passenger ships, will not have this nuclear system because of reactive things. But naval system, aircraft carrier and submarines, many applications, nuclear fuel will be there. So there will be nuclear engine, because there will be no emission or like say carbon dioxide, any other fluid will be going out from here, so no one can detect it also. Okay, so naval ship submarines powered by nuclear fuel, pressurized water reactor. So these are pressurized water, okay, and this water is kept under pressure to prevent boiling and avoid. Okay, so pressure will be very high so that no boiling will be there. Okay, in cycle or loop A, the hot water from the reactor heats a separate water circuit in the steam generator. Okay, so you have two circuit, one circuit A, another circuit B. Binary cycle power generation system for ship process test. Okay, so I got from one news item. So they have used binary power cycle for their marine vehicle. Okay, class NK, this classification type ship. Binary cycle power generation system uses water waste heat on ships. So wherever waste heat is there, for example, you have any boiler system, you have extra exhaust gas or IC engine, so that exhaust heat or waste heat can be used to run another steam turbine system where you can generate some certain amount of energy. So it generates 100 kilowatt power. The electricity will be serving as auxiliary power to contribute efficient energy utilization and reduce carbon dioxide emission. Okay, so normally that waste heat can be utilized to drive a turbine system, and you can utilize for your shipping and many other purposes. Okay, binary vapor cycle fluid. Steam normally will have critical temperature 374 degree. This critical pressure is 2 to 5 bar and 374.15 centigrade. Okay, this create difficulty in design operation control. So mercury diphenyl oxide, similar compound, aluminum bromide, zinc, ammonium chloride, these are fluid can be used for as a one fluid, another fluid can be water. Okay, so this binary cycle means I will have two vapor envelope, one is here, another is here, TS. Okay, because you have seen like one. Okay, I'll draw the cycle also. Let's say this is my reactor. Okay, it will be driving one turbine, then it will have one condenser, simple Rankine cycle I am assuming, pump. Okay, and this can be like say sodium cycle possible, because very high temperature sodium can be liquid like water. Okay, now I have one heat exchanger. So this heat exchanger, this is heat. This heat exchanger temperature also very high. Okay, so this will be used to increase your water temperature. Okay, pump, condenser, so I can put some name also, right? One before turbine, then 2, then 3, then 4 for my sodium cycle, and for my water cycle I can put similar nomenclature, 4, then 5, 6, 7, 8. Okay, now sodium cycle temperature higher, so TS diagram, my cycle will be up, right? So let's say my sodium cycle is here, maybe some superheat also there we are assuming. Okay, then turbine is taking power, then condenser will be condensing. Okay, then where is my pump? Okay, so where is my one is here. This is this is sodium cycle. Fine. 1 2 turbine, 3 2 to 3 my condensation happening. Okay, 3 to 4 pump working, 4 to 1 again your heating happening. This is happening inside reactor. Okay, now 2 to 3 the top cycle is releasing heat, so bottom cycle will be absorbing heat. Okay, so bottom cycle will be absorbing, so 5 8 to 5, right? So 8 to 5, I'm assuming everything is ideal. 2 this is 5, this is 6 7 8. Okay, so this is H2O cycle. So two cycles together. So first cycle maybe it is harnessing some energy or extracting some energy from the fuel, from the fluid. H2 also extracting certain amount of energy. Okay, now you can see that 2 to 3 heat released, LEASC by NA loop, right? So 8 to 5 heat absorbed by H2O. Fine. So from reactor, water is not giving directly, taking directly energy, rather some one loop is taking energy, it is giving to another loop, maybe several other loop also you can create based on your temperature. Okay, let's assume we have only two level. Okay, now mercury can be possible, sodium can be possible. Mercury is the only working fluid successfully used practically due to high critical temperature 580 degree and lower critical pressure. Binary vapor cycle increase overall efficiency, eta. Two fluid, mercury and water are used. Okay, so mercury also can be used. Fine. Binary cycle working fluid property. High critical temperature must be there, reasonable low pressure must be there, high heat of vaporization for minimal fluid weight, freezing temperature below room temperature, chemically stable. So many other properties are there, just you can go through it. So mercury favorable characteristics also there, like normally it will be liquid in normal temperature, but at high temperature it can be evaporated also. Okay, so some disadvantages also there. It does not weight metal surface, so hindering heat flow rate. Okay, so because it is not weighting, so heat transfer will be lower. Okay, adding magnesium and titanium, this very small part also will be helping to improve heat transfer rate. Okay, binary cycle overall efficiency. So how to calculate overall efficiency for two cycles? Okay, so first you draw the two cycles, TS diagram. TS. Okay, so I'm drawing the cycle again. I will have one pump here. Okay, so this yeah, so the point 1 is here, 2 is here, 3 is here, 4 is here. Okay, then other cycle is one is here, other cycle C, D, A, B. Okay, now eta equals W by Q, net work output divided by heat input, right? So eta, this is a P cycle, this is Q cycle, we are assuming. So eta P equals WP by QP input, and eta Q equals WQ and QQ. Okay, now total work output, W equals W1 plus W2, or WP and WQ we can add. Okay, now eta Wp plus Wq by Q1. Q1 means actually you are giving 3 to 4 heat energy. Okay, total energy is coming from reactor only. So this is reactor or any high energy source where very high amount of heat is there. So you are not running only one cycle, rather you are creating 2 cycles or 3 cycles for binary system. Okay, so first cycle is taking heat and other part automatically running. Okay, one releasing, another accepting, one releasing. So that way it is working. Okay, and we are assuming this 2 1 Q2 to 1 equals QB to C. To which is higher? Higher is 1, right? Or I'll write heat rejected by P equals heat received by Q cycle. Okay, so both cycles are there, one is rejecting, another receiving, same amount. We are assuming there is no losses. So eta equals Q1 eta P plus Q2 eta Q by Q1. You can see here W, it is coming like this, Wp equals eta P Qp. Okay, so Qp actually Q1. Okay, because upper cycle total energy input is happening here only, right? And Q2 eta Q equal Q2 eta Q equals WQ. Okay, so both are put, we have given here, and we are getting eta equals Q1 eta P, Q2 eta Q. Now eta P, this is Q1 plus Q2 by Q1 eta Q. So eta P plus Q1 minus W1 means WP by Q1 eta Q. So one eta P plus eta Q, you can see eta Q minus WP Q1 eta Q. So it is giving eta P minus eta Q minus eta P Q1 by Q1 eta Q. So after solving this one, we are getting eta equals eta P plus eta Q minus eta 1 eta P eta Q. Okay, so this is your formula. If binary cycle is there and if efficiency given for cycle 1 and cycle 2, so combined cycle efficiency you can calculate from this formula. Again, Brayton-Rankine cycle. So in previous part you have seen Rankine-Rankine. Now you have Brayton-Rankine cycle. So you have some waste heat and you want to run another cycle. Okay, so normally the Brayton cycle will be running at higher temperature. Okay, so high temperature means I have one compressor, I have turbine connected, I have combustion chamber C1 T1 or GT1, and this is giving, let's say, heat rejection here. Okay, so this is rejecting heat here. Number is A, B, C, D. Okay, now I have another cycle here. Steam turbine, I am writing ST. Okay, ST1 maybe. And in this case, I have one pump. Then I have heat exchanger here. So heat is getting rejected here. Okay, numberings are here 1, 2, 3, 4. now you can see this top one is gas turbine, this is steam turbine. Okay, if you have any high heat source, steam turbine, or it may be possible that ice engine is there, it is having lots of waste heat, so that also can run one steam turbine system. Okay, so anywhere if you find any waste heat is there, you can boil it, you can run one system which will give power. So it will be normally, it will be like Rankine type cycle. Now TS diagram if I draw, now if I draw TS diagram, you can see this Rankine cycle will be running at lower temperature, but Brayton cycle will be running at higher temperature. So first draw Rankine cycle envelope. Okay, and it is like this. Okay, 1 2 3 4 as per your cycle diagram. Now where is gas turbine cycle or Brayton cycle? It is here. A, B, C, D. Okay, now what is happening? Heat rejected by GT cycle, Brayton cycle equals heat received by Rankine cycle. Okay, so this is GT, this is steam turbine or Rankine. Okay, so so you should not get confused, steam turbine or Rankine cycle, gas turbine or Brayton cycle. Okay, now overall efficiency also it will be following same rule, eta 1 plus eta 2 minus eta 1 eta 2. So whatever you have derived for previous case like Rankine here, Brayton-Rankine also will have same formula, so you can derive also. Okay, okay, so organic Rankine cycle, organic Rankine cycle means like you are using waste heat to run a Rankine cycle, so they put the name organic Rankine cycle. So similar to Rankine cycle, uses lower boiling point organic fluid suitable for lower temperature heat source. Okay, so somewhere you have some small amount of heat source, so you use lower boiling point system and you increase, you boil certain fluid and you get energy from there. And one good example is that we have OTEC system, ocean thermal energy converter. So there what they do, they will have sea floor temperature about 4 degrees centigrade, you know that, because high density of water temperature will be 4 degree, but sea surface temperature will be like about 30 degree or 28 degrees say. Okay, now this 4 degree and 20 degree temperature difference is very low, but in gas turbine system or steam turbine system your temperature difference was maybe 100, 200, 400 degrees centigrade. But in OTEC system, ocean thermal energy converter system, your temperature difference only 20-25 maximum. So the NIOT, National Institute of Ocean Technology, they designed their OTEC, ocean thermal energy converter, to produce desalinated water for Lakshadweep Island, and their system was running about 18 degree temperature difference. Okay, so within 18 degree you cannot boil your mercury or sodium, or you cannot boil your water. So what they do, they'll be using ammonia, okay, as a working fluid. So what they do, they will have one pipe at lower temperature. So let's say any fluid you take, ammonia or any refrigerant, I'll be teaching later. Refrigerant means like those fluid will be creating vapor and liquid if you change pressure and temperature. So low, at normal temperature it may be gas. If you reduce temperature further, like say 4 degree, then it will be liquid. Okay, so at 4 degree it will be liquid. Pump it, okay, pump it to the surface, and there you put on turbine. Okay, so turbine, then what will happen at surface at high temperature, 28 degree temperature, that ammonia or other fluid, it will be gas. Okay, so gas, when it is passing through turbine will be giving energy. Then after turbine you put the same one through another pipe to this seabed again. Okay, so in your steam turbine, if you remember, or you see this picture also, pump is here, condenser is here, turbine is here. Okay, so condenser, where condenser will be there, my condenser is a seabed. Okay, you can link it. Okay, turbine is on the surface, and pump, there must be pump somewhere here. Okay, so pump can be somewhere here. Okay, up, because pump will be delivering only liquid. So 4 degree centigrade temperature, make refrigerant or ammonia liquid, then pump it to surface, run your turbine, then after turbine again re-inject that fluid into seabed through on pipeline. So that way the OTEC system will be working. So NIOT, National Institute of Ocean Technology, if you visit sometime, you can see their system actually. They have already deployed in Lakshadweep area. So the temperature very low, so system performance also very low. But people say like, because it is free energy, you are not, once you install things, then after the things will be running automatically. You do not need to invest again. So that's why many people are interested to develop ocean thermal energy converter also, like Japan, US, India, many other countries also there. They're trying to develop or trying to harness ocean thermal energy through Rankine cycle. This is also Rankine cycle. Okay, practically NIOT applying.